Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered if different groups of people have different ways of thinking about things like mental health or even personality traits? Well, today we're diving into a fascinating study that tackles just that, using a cool new way to compare complex patterns of information. This paper introduces a method to check if two groups of people have the same internal map of how certain things are connected. Think of it like this. Imagine trying to map out how different anxiety symptoms are linked together in someone with anxiety versus someone without. Do those connections look the same? Or are they wired differently? That is the big question these researchers are exploring. So, how do scientists usually do this kind of comparison? They often use what is called a network comparison test, or NCT for short. The NCT is great because it tells you if there is a statistically significant difference between two networks, but it doesn't really tell you how much they differ. It is like knowing your car has a problem, but not knowing if it is just a squeaky brake or a full engine failure. That's where this new study comes in. They've built on a cool idea from previous research called the SF similarity metric. This metric, SF, can actually tell you how similar two networks are. But the original recommendation was to only use SF after you already knew the networks were different from another test. Which is a bit like saying, only look at how badly your car is damaged after you've already confirmed it is not roadworthy. What these authors have done is create a new test. They call it the NCT-sF. It combines the rigor of the NCT with the insight of the SF metric. This means you can run one test and get both the answer to, are these networks different? And if they are different, how different are they? It's like getting a diagnostic report for your car that tells you both if there is a problem and exactly how severe it is. Let's quickly talk about what a psychometric network is. Imagine a bunch of dots and each dot represents a symptom, a personality trait, or some other psychological concept. Now, draw lines between these dots and the strength and direction of those lines show how strongly those concepts are related to each other. For example, you might see a strong connection between feeling sad and lack of energy in a network of depression symptoms. Usually, researchers build these networks from data collected from one group of people. But really interesting questions come up when you want to compare how these networks look across different groups. Think about it. Do people experiencing depression have a different web of symptom connections than people who aren't depressed? Does therapy change the way symptoms of a disorder are linked? Does how people from different countries experience stress differ in their underlying symptom networks? These are the kinds of questions that drive psychological research. The traditional NCT works by shuffling the data around many times. It's like taking all the people from Group A and Group B, mixing them all up, then randomly splitting them back into two new groups of the same size. They then build networks from these new randomly created groups and see how different their networks are. They repeat this thousands of times to get a sense of what kind of differences you'd expect to see just by random chance. If the real difference between the original Group A and Group B is much bigger than what you see from random chance, then you can say they are statistically different. Now, about that SF metric, it's based on something called the Frobenius norm. Don't worry too much about the math for now. Think of it as a way to measure the distance between the matrices that represent the networks. A distance of 0 means the networks are identical. The SF metric then takes this distance and turns it into a similarity score, where 1 means perfectly similar and 0 means completely dissimilar. The problem was, SF can be a bit tricky to use on its own, when you are looking at actual data, not the perfect theoretical networks. SF might show a slight difference even when the underlying populations are actually the same. This is why the previous advice was to use it only after verifying a significant difference with something like the NCT. So, the brilliant part of this paper is that they figured out how to use SF as the thing they're comparing in their shuffling process. Instead of just looking at the biggest difference in any single connection or the overall strength of the network, they use the SF score itself. Here is how their new NCT-sF test basically works. First, they estimate the networks for Group 1 and Group 2 from the actual data. Then, they calculate the SF score between these two networks. This is their observed difference. Next, they take all the data, pool it together, and randomly split it into two new fake groups, keeping the original group sizes. They build networks from these fake groups and calculate the SF score again. They do this shuffling and recalculating process thousands of times. Finally, they compare their original SF score to the thousands of SF scores they got from the shuffled data. If the original SF score is very low, meaning high difference, and only a tiny fraction of the shuffled SF scores are as low or lower, then they can say the original networks are significantly different. This figure here visually explains that shuffling process. You have your two original groups, You pool the data, then you shuffle and split many times, calculating the statistic each time to get a distribution of what differences look like by chance. To see how well their new NCT-sF test worked, they ran a large computer simulation. They created artificial population networks with some differences built in, and then they simulated collecting data from these populations with different group sizes. They compared their new NCT-sF test against two other standard NCT tests, NCTI, which looks at the largest edge difference in NCT, GS, which looks at the global strength of the network. First, they checked for type 1 errors. That is when you incorrectly conclude there is a difference when there isn't one. Think of it as a false alarm. The good news is all three methods, including their new NCT-sF, did a great job of controlling these false alarms. They kept the type 1 error rate right around the expected 5%. That means their test is reliable and doesn't go off screaming difference when there's actually no difference. Now, for the powerful part, power is the ability of a test to correctly detect the difference when one actually exists. They first looked at what happens when only one single connection between two variables is different between the groups. In this specific scenario, their NCT-sF test wasn't as strong as the traditional NCTI test. It had lower power, especially when the difference in that single connection was small. You needed larger sample sizes and bigger differences for NCT-sF to really pick up on it. The NCTI, which just focuses on the biggest single difference, was better at catching these isolated changes. But here is where it gets interesting. When differences were spread across multiple connections in the network, the NCT-sF started to shine. In these cases, it often performed just as well as NCTI, and in some situations where the differences were moderate but spread out, it was even slightly better. This is a key finding because often psychological phenomena are complex, with many small interconnected changes rather than one giant one. The NCT-sF is better at capturing these more nuanced, widespread changes. It also showed good power when a larger percentage of the edges were affected, even if the individual changes were small. To show this in the real world, they applied their methods to data on eating disorder symptoms in individuals with and without depression. They built two networks, one for each group, representing how different eating disorder subscales are connected. Visually, you could see some differences. The network for depressed individuals seemed to have more negative connections, meaning as one symptom went up, another symptom tended to go down more strongly. When they ran the tests, they got different results. The traditional NCTI, which looks at the biggest edge difference, and NCT-GS, which looks at the overall strength of connections, found no significant difference between the depressed and non-depressed groups' networks. But their new NCT-sF test did find a significant difference. This means that while the biggest single connection difference might not have been huge, the overall pattern of connections across the entire network was different enough to be detected. And remember that great benefit of NCT-sF, it provides an effect size. The SF value of 0.73 told them something about how different the networks were, giving them more insight beyond just a yes or no answer. So, to sum up what they found, their new NCT-sF test is a reliable way to check for differences between networks with good control over false alarms. When only a single connection is different, the older NCTI might be more powerful, but when differences are spread across many connections, North Carolina TSF performs just as well as NCTI, and sometimes even better, especially for moderate. Widespread changes. Crucially, North Carolina TSF gives you that valuable effect size, telling you how much the networks differ. What does this mean for researchers? Well, it gives them another great tool. They can now use NCT-sF to not only test for differences, but also quantify them. This is super important because, as seen in their example, different tests can sometimes give different conclusions. They suggest researchers could run all three tests, NCTI, North Carolina, TGs, and NCT. SF and then discuss how the results align or differ. You might even want to adjust for running multiple tests to be extra cautious. The biggest win here is the interpretable effect size. Knowing how different two networks are is often just as important, if not more important, than knowing if they are different. It allows for a deeper understanding of the phenomenon being studied. Now, it is not perfect like most statistical tests. North Carolina TSF still needs decent sample sizes, and the bigger the difference between the networks, the easier it is to detect. They recommend at least 500 people per group for these kinds of comparisons, which is a bit more than previous recommendations, suggesting that these network comparisons can be quite demanding. They also point out a few limitations. Their simulations mainly use dense networks, meaning lots of connections between variables. They're not sure how well NCT-sF would work with sparser networks. They also only tested this with continuous data, not binary data, and of course North Carolina TSF is for comparing distinct groups. If you are interested in how things change over time, or with continuous variables like age, you'd need different methods. They also briefly touch on using these methods with data collected over time. While their current test is for comparing distinct groups at one point in time, they suggest that the core idea could be adapted for paired data, like comparing the same individuals before and after treatment. That is a really exciting avenue for future work. In conclusion, this paper offers a valuable new tool for psychologists. The NCT-sF provides a more nuanced and informative way to compare psychological networks across groups, allowing researchers to not only detect differences but also understand their magnitude. It's a step forward in understanding the complex web of connections that underlie our thoughts, feelings, and behaviors. So what is my take on this research? I think it is a really clever extension of existing methods. The ability to get both a statistical test of difference and a meaningful effect size all in one go is a big win for clarity and interpretation. It feels like we're getting better at seeing the finer details in psychological data, not just the big obvious shifts. The limitations they mention, like the need for large sample sizes and the focus on continuous data, are important to keep in mind. It reminds us that no single method is perfect for every situation. But for comparing stable group structures, this NCT-sF seems like a really promising approach. What future research could do is explore how this works with different types of data, like binary questionnaire responses, and really nail down those cutoff points for interpreting the SF values in different contexts. Imagine being able to say, this difference in symptom networks between two groups is equivalent to X amount of change. That is powerful stuff. This research helps us understand how different groups might process the world or experience psychological phenomena differently, not just on a surface level, but in the very structure of how their internal concepts are organized. It's a reminder that underneath our shared humanity, there can be subtle but important differences in how our minds are wired. What do you all think? Have you ever wondered if your own mental map of something is different from someone else's? Let me know in the comments below if you enjoyed this deep dive into research. Please give this video a like and subscribe to RUBIN'S Mind Lab for more explorations into the fascinating world of psychology. Thanks for watching, and I'll see you in the next one.